Good morning and welcome to another MEscope webinar. Thank you for joining us. My name is Mark Richardson, Marketing Manager with Vibrant, and I'm joined by my father, Mark Richardson Sr., President and CEO of Vibrant Technology. And we got another good one for you this month. Today's topic is called, Can Repeatable Vibration Results Be Obtained from Cell Phone Videos? So, gosh, I hope this works. Obviously, we've been doing a lot more with cell phone videos lately with MEscope, and it's really been a popular tool for a lot of our customers, and we continue to push forward with it. A couple things before we get going here. I did want to mention, if you are needing any MEscope training, there is a hands-on modal and ODS training course coming up in Southern California on November 17th through the 20th, given by our partners at NavCon Engineering. If you want to get more information, you can go out to their website, navcon.com. That's NAVCON.com. And you can get more information on that training course that's coming up here in November. I believe they still have some seats available. A couple of housekeeping items before we get going. We will be recording this video, and we'll get this posted out on our YouTube channel sometime next week. And if you want to go back and review anything or have any questions, you can always jump back out there and see a recording or see a recording of all of our past webinars. In addition, if you have questions during today's webinar, we will hold the questions until the tail end of the webinar. And you can go ahead and type those questions into the dialog box there on the right-hand side of the GoToWebinar panel. With that, let me hand things over to my dad, and we'll get going here with the webinar.
Thanks, Mark. Welcome to all of you. One other thing to add to what Mark already said, we do have a package on our price list, and you can inquire about it. But if you buy our basic modal with the video processing, we give you a free seat in the NavCon modal analysis, hands-on modal analysis training class. It's a 4-day class here in Southern California. There's one coming up in November. I think there's still available seats. So if you get excited about what you're going to see today here in a few minutes and want to start processing videos, either with a high-speed camera, it doesn't matter what camera you use to record a digital video. All this technology is moving very quickly now. The cell phones are getting better. Next month, we're going to compare results from a Google phone with an iPhone. Now, what I'm going to show you today is using 2 iPhone videos that I recorded here on a rotor kit, and I'm also putting together with today's topic an app note. So anyone who owns MEscope can go onto our website with a valid license and access our app notes, and you can see we've got 60 of them. This will be our 60th app note. Those are very useful for learning all the ins and outs of using MEscope. MEscope is a toolbox, and there's over 500 commands in it. So it's I liken it to Microsoft Word. I only know about 10% of Word, the commands in Word, but I can get my job done with it. MEscope is similar in that we've got a lot of capability built into it, but in order to get an animated picture, in what we call a video ODS, if I'm extracting data from a video, that's really what you want to focus on, getting to that animated picture as quickly as possible so that you can show, vibration problems to your boss, to maintenance management, to operations management, to your clients, your customers. That's where MEscope is really a useful tool. You can take your cell phone out of your back pocket and put it on a tripod. And there's all sorts of things. There's lighting issues. We'll bring some of that up maybe in next month's webinar. My son Sean will be helping me with that, and we'll compare some higher speed videos from the two different cell phones where light flicker and things like that become an issue. They can be solved, but we're going to look at videos that were processed at 60 frames a second. And that is a slow enough speed to look at a lot of machinery vibration, and you don't have a flicker problem with internal lighting in a room or in a building. Anyway, this is the beginnings of this app note. Here's a picture of the machine that we're going to look at here. Look at the videos of it in a minute. And you can see over here, there's some little screws that you can screw onto the two rotors to create unbalanced conditions. Now, we're not so much interested in detecting unbalance from the ODS. That was the topic of last month's webinar, and you can go to our website and download a recording of that webinar. And so we discuss being able to uniquely identify unbalanced conditions from cell phone videos. So that's pretty interesting. Let me put that down. Let me show you one of these videos here, and this one will be animating. And so this is the raw video, what we call a raw video. And you can see the rotors moving. You can see the videos captured a little bit of the unbalanced screws that are screwed into both rotors. And of course, you can see the coupler. So that's one of them, and that's about 30 seconds, 35 seconds of a recording. So within a minute, you can record. Here you can watch the time here. It's a little over, it's about 35 seconds. They're both roughly 35 seconds. Now, what I'm going to do with that, and that's quite a long video. You can get plenty of vibration off of a 10-second video. But with 35 seconds, we're going to remove some of the original frames, the starting frames and the ending frames, because I use my finger to start the recording of the cell phone. So there's a little bit of vibration due to my finger at the beginning and at the end, and I want to remove that from the processing of the video so that that doesn't impact the results. But you can use a Bluetooth, a little $25 wireless attachment to your cell phone so that you don't have to touch it. And there's other things. There's stable platforms. Of course, there's lighting. We sell lighting, and we sell a high-speed camera also that will go up into the kilohertz region. The cell phones are limited to 240 hertz maximum. But times 60, that's 14,000 RPM. So that covers a lot of machinery vibration problems. Okay, so let me bring up MEscope here, and I've already got it open to a project, and this project is called One Screw Both. That means I put a screw, an unbalanced screw into both rotors, and so this project will also be attached to the app note. So if you have an MEscope license, you can download this app note, download this project, and go through all the steps. So let's start out with what we call our video wizard. I'm going to click on that. You can see I'm using the ribbon. Now, many of you are using MEscope. You're probably more familiar with just the menus, and you can use menus, and all the commands are up here in the menus, but I like the ribbons because there's a little bit of graphics. Okay, so here is the beginning of the videos wizard. I'm going to click on open raw video, and here are these videos that I took. Baseline was no screws, one screw on both rotors, one on the inner one on the outer, and then 2 screws on both rotors. So I'm just going to open up one of these, and we'll just walk through a few of the steps of the wizard, and I'll show you. And this is all in the app note again. So here it is, and you can see there's several things we can do here. There's 5 steps to the wizard. This is step number 1. We can adjust brightness, we can adjust contrast. So I've adjusted both of these. If I, change the contrast, it gets really dark. So if you've taken a video that kind of looks like this in the dark corner somewhere, you can brighten it up right here in the wizard, and the algorithm that extracts the time waveforms from your video is based on a color variation of pixels from one frame to the next to the next. That's basically how it works. So that's built into MEscope, and there's other people that'll tell you, well, you should just use black and white. Then you lose all the advantages of color when you want to show results to your boss or a customer. So we just use the raw video, and the algorithm works just as well with a color variation. So we'll see that in a minute. The other thing that I want to do is crop out any of the background that's not of interest to me. The only thing that's of interest is the vibration of this rotating machine. I want to see what it vibrates like. So now what I did by cropping it is I eliminated a lot of pixels. So what the algorithm does is it processes all the pixels in each frame, and you can go down here. Let me go back and I'll reset the crop. You can see that there's over 8 million pixels per frame, and that's right out of your cell phone. So when you make a video, you are recording in the electronics of the phone 8 million pixels per frame, which is pretty amazing technology. I want to eliminate that. I'll cut it down in half by just cropping the picture, and we'll get down here to the test article of interest. And then I'm going to hit the next button. So the next step here says frames and elapsed time. So this is where I want to remove some of the beginning frames and ending frames because there's vibration in there due to me touching the cell phone. And of course, it's very sensitive. So if I cut this down by dragging these little bars here, you can see that I can, if I drag it way down and remove a lot of the frames, I only have 8 seconds of data. Well, that's not going to be enough to do some of the processing we're going to get into to calculate some what we call ODS-FRS. But the other thing is I want to put in the capture frame rate, which is right off of the cell phone, 60 frames a second. So I've got about 2,000 frames. That's a lot of data. So I'll be able to do spectrum averaging off of these time waveforms. And that's pretty much what this step requires. And again, if I see anything that I don't like in those frames, I got a button here called check frame validity. We could go through that, but it's just something that happens in the background that looks for errors that can come out of the cell phone or out of your recording. Now, this is something that's unique to MEscope. Of course, any of you that own MEscope know that you need to build a model if you want to look at your ODS or your mode shape data. Your model consists of points, lines, and surfaces. Well, we use the same capabilities to create a surface, and we call it a point grid. So you can see this is step number 3, and I can change the number of points in the point grid. Now that will cut down the amount of data that I extract from the video because I'm only going to get a time waveform for each of the points in the grid, the X motion and the Y motion, horizontal and vertical motion. But in this case, and we're going to jump ahead here and look at the results. I'm going to get all the way up to 14,000 points. Now, even that, you can look up here. What we're going to focus our attention on is the vibration of 2 points on the motor. And we put accelerometers on those points and measured the vibration with accelerometers, and 2 points, one on each of the bearing blocks. So we've done some testing with this machine, comparing acceleration to videos. Today, we're just going to go through and pick a point out of the grid here, so we can get the motion of just 4 points. 1 point on the beginning or on the front and on the back of the motor, and then a point on the top of each bearing block. And that's going to form our ODS with X and Y motion at 4 points. Now, this is the most time-consuming step in the wizard. And if I hit this button here, extract time waveforms, I'm going to go through almost 2,000 frames. The software will do this with about 3 million pixels per frame. And then it's going to assign that motion to 14,000 points in the point grid. And that's going to take about 10 minutes on my computer. Now, the newer computers that have the NVIDIA hardware in them, we've got customers reporting that it's much faster with a new computer. The NVIDIA, if you're familiar with NVIDIA, they're making hardware chips for graphics. They're basically graphics processing chips. So I'm not going to hit this because we'll be sitting here having another cup of coffee waiting for this to finish. So let me just close this and let's just go look at the results that we've already extracted from the 2 videos of this rotor kit. So I'm going to say, yeah, I want to stop. Now, if I go to my hotkeys here, this is a standard feature in MEscope. Each of these hotkeys has what we call a script. And if any of you have written scripts in Excel or Word or any of the Microsoft tools, or Apple, I think, has some scripting in it, it's the same thing. I'll just show you one of these. I'm going to hold down a key. And so here's a script, and it's just a target window, a command in that window. I can open dialog boxes and then a description. So very simple. They're easy to build, but you know, most of our customers don't want to do that kind of thing. It's programming. You have to scratch your head and think, well, what do I want this thing to do? Well, a lot of the commands are just positioning the windows so you can look at your results. MEscope is a graphics tool. And then starting the animation is the animate a shape, set the speed, set the amplitude. So those are the kind of things. When I hit this hotkey, now, again, I got a reset key in here. This is really nice. We put this into all of our app notes now, and our, I think even in some of our, these are demo projects that when you get MEscope, you can just go click on any one of these. They all have hotkeys in them now and scripts, and you can just run them. So for modal, you can go in here and you want to see how the curve fitting works. I think there's 3 or 4 different curve fitting examples in here. ODS animation, we got various models with different animation, and then some video ODS projects. Those are all VT Max projects that if you click on a button, it'll just bring it up. These are our demo projects. Then I'm going to go up here and click on video 1 because these are the results of processing the first video in the wizard. And as I said, it took about maybe 10 minutes to extract the time waveforms from the video. But here's what you get. When you come out of the wizard, you always get 3 data files: a structure window, which is a standard structure window, with frames of the video pasted right onto the grid the rectangular grid, and it starts a sweep here. And you can see in this case, we got 13,000 time waveforms here. So that's the raw data that was extracted right off of the video, and each sample in the time waveform corresponds to a frame of the video. So you can see the animation when I sweep through the time waveforms is actually changing the picture and putting the frame of the video that the time waveform came from right on the animation. So that captures everything that we recorded in the video. Down here, these are the DFTs. Now, a DFT is a discrete or a digital Fourier transform. And we get one DFT. You can see I got 13,064, 13,064 of these. So there's a Fourier transform for every time waveform. And I can go back and forth. MEscope has an FFT built in, so I can, just like in a spectrum analyzer, I can go back and forth. Now, the advantage of the time waveform is, of the DFT, is that I've got peaks in here. So here is the running speed. That machine was running at around 1,000 RPM when the data was recorded. And this is what the ODS looks like from the frequency domain. Well, you can see that there's a mode shape of that rotor there. You might call that first bending. There's some complexity in it. Both of these rotors are rotating or animating with sinusoidal animation, and even the shaft itself has got some motion in it. Now I can crank this motion way up, or I can just drag this over. This is very interactive. There is another peak. There's a very big peak. Well, I can see that peak of vibration, again, this is what we call an envelope here. Let me see what happened here. Let me draw the envelope down, because the envelope will show us what's in the data. Okay, so here is an envelope. Well, let me move on. We're not quite seeing what I expected to see here, but we're gonna do some calculations here in a minute, and we'll see more of the details. Let's go to the next step. Now I can come back here, the second video, very similar result. It's just different data, but it's going to look pretty much the same. Let's go on and pick some monitored points from the first video. So these are tools in MEscope. You need to be a little bit familiar with them, but basically what I already told you, we're going to pick 4 points on the machine. So here are all the points. Now I also didn't mention that in the wizard, there's a step where it's actually the last step of the wizard, and we didn't take that last step. Now in the app note, you'll go through that. But the points with the lowest motion, what we do, we take all the magnitudes of all the 13,000 points here, or in this case, it's 6,000 points. It's half the number of time waveforms, so 6,500 points that are still animated. But the grid had a lot more points in it, but we've hidden the ones from the background and some of them from the motor, because the algorithm can't measure vibration when the picture is all black like this. So a lot of these points have been taken out because there's no change in the picture from frame to frame to frame. But anyway, we got plenty of points up here around each of the accelerometer locations of the machine, and certainly on the top of the bearing block. So I'm going to crank this up a little bit. I'll go to animate, and let's increase the amplitude. So now you can see the whole base plate is just rocking on the rubber mounts. And of course the rotors and the coupler are dominating the ODS when I crank it up, but what I want to look at is the ODS values of the motor and the bearing blocks. So let me just stop that. And now I'm going to go in and grab one of the points. And, you know, I can go back and forth here, but I'm just going to grab a point off of the grid. And we're just going to go through and use those points. And let me just grab 4 points. You can see I got the interactive point selector on down here. It says select objects. I got a little floating, and I can do a bunch of different things with this little floating dialog box. This is all standard stuff in MEscope for. Now I didn't like that one, so I'm going to click on it again. Oh, okay, I got some points that I didn't like there, so I'm going to just get one that's away from this rotor, because these points over here are going to be influenced in the algorithm by the motion of the pixels from that rotor. So let me just pick one over here a little bit out of the way, just to be on the safe side. So I got 4 points. Let me see if I got all 4 of them. Oh, I got 5. Oh yeah, here's one right up here. So I want to get rid of that guy there. I don't know where he came from, but if I turn off my point selector now, when I click around, I won't get any more points. So there's my 4 points. Now let's just take a closer look at them. Let's turn on the point labels. Okay, there they are. Those are their numbers. You know, I got thousands of points in this grid. So, but I want to change those to, in order to compare ODSs, I'm going to number them 1 through 4. So let me just do that. This one here, the 2455, I'm going to number that as number 1. And then 1860 is going to be 2. 1661 is going to be 3. And 1440 is 4. So there they are. Now let's turn on magnitude and phase for those. We already got the ODS. We're already doing video ODS here. This is animating with my data, and I can go over here and I can even, you know, color those 4 points, and we'll make them red, and we'll make them a little bit bigger so we can see them. Okay, so there we go. And if I turn the animation back on, take it off, pause, continue. So now we focused on, and it looks like I picked some good points. Not a whole lot of motion on this. And let me just decrease the amplitude here so those rotors are not in the way. But now you can see magnitude and phase. Now this is something machinery people are really interested in. If you look at the X direction, and again, we're animating off of the running speed, this peak down here, this order peak, you can see in the X direction, phase is the same on the motor, and it's the same on the inboard, but outboard is like 90 degrees different. And then in the Y direction, which is the vertical, they're all moving, these are 90 degrees apart now. So again, if I increase the amplitude, you know, I can see that really clear. And then if I go to one of these other peaks over here, which is another order, you can see the magnitude and phase is all changed. So machinery people want to know, what is the difference between the magnitude and phase of points on the motor versus points on the pump or the gearbox? Here we got the graphics right here in front of us. Okay, well, let's move on to the next step, and let's compute some ODS FRS for those 4 points. So I'm going to go to this hotkey, and it's going to take that model with the points that I selected, and there they are, and it's going to do some processing. Now, what it's doing in the background here, and I can show you my script. It's a little bit complicated, but it is actually computed what we call an ODSFRF. Now, when we can't measure the force that causes this vibration, we call it an ODSFRF. If we can measure the force, which we do with an impact hammer or shaker or multiple shakers or multiple impacts, then we call that an FRF. And to get mode shapes, we normally curve fit FRFs, but we have to have the response divided by the force. What we're looking at here are ODS FRFs, and we only have 8 of them. If I look in my properties spreadsheet here, you can see I got, well, this 9th one here is an envelope, but I got 8 of them, and you can see they're labeled with 1X, 1Y, up to 3, and the reference is 3Y. So same as a cross spectrum. ODSFRF is a little different than a cross spectrum. I can integrate and differentiate ODSFRFs. And these are in units of, let's see, is it saying what units they should? Oh yeah, inches per second. So what we did is we took the displacement data, and here are the time waveforms from those 8 points up here, and we can animate them too. So now I got a sweep cursor going through where I can stop it anytime I want and put a dwell animation on, but that's a time-based ODS from those 8 points. Magnitude and phase, we're displaying that, and of course the phases are all just plus and minus, 0 and 180. Down here, I got different phases and different magnitudes, but they're in units that a machinery guy would, let me just stop this so we can talk about this for a second. A machinery guy would look at this and, you know, this vibration is 1/10 of an IP at the running speed. That's certainly safe. When the vibration gets up to an inch per second, again, we're using English units here, that means the machine is about ready to fly apart or go through the ceiling in the building. So that's another, in addition to looking at phases, now these phases are all, we want to talk about relative phase because they're all relative to 3 in the Y direction. We use that as our reference response. So you can see all that in the spreadsheet here. The properties of these ODSFRFs are, you know, 1, 2, 3, 4 in the X and the Y, all relative to the Y. So if I click here on the Y, the magnitude is the auto spectrum of that response. But if I look at the phase should be 0. So let me just show that here real quick. Phase, there it is. The phase is 0 because it's relative to itself. So what we're looking at here is, let me just put it back, magnitude. We're looking at the data for the 8 points. And here is a good look at these 3 peaks. So again, what the ODSFRF is showing us, we got something selected here, just point 3. We want to see, there's the ODS for that peak. Now, what is that peak? That peak is 16,580. Well, the maximum frequency, and we call that F max of this data, is 1800 RPM. So just thinking out loud here, the data was recorded at 60 frames a second times 60. That means the sample rate of this data was 3600 RPM. And then in the frequency domain, one of the rules of the FFT is that the spectrum, any frequency data, is 1/2 of the sample rate. So the maximum frequency, what we call F max of this data, of the ODS FRFs is 1800 RPM. So, and this is the running speed of the machine. So that's a pretty good tachometer in itself. It is just showing that this machine was running at 972 RPM. So if you do some simple math, the second order is going to be twice that, which is 1900 RPM. Let me get my calculator out here real quick and we'll do the math. So 972 times 2 would be the second order. That's at 1944. Now that's beyond the frequency range of this data, but what happened is that it aliased around 1800 RPM. We don't have any anti-alias filters in a video. So this is another, you might call it a limitation of the video, but in fact, the video has captured all the vibration between 1800 RPM and 3600 RPM, only it displays it in a different place. So if I take the 1944, which is what the frequency of the second order is, and I subtract 1800, now let me go back here, 1800, which is F max, that gives me 144 RPM. And now if I subtract that from 1800, because it wrapped around the 1800, I get 1656. There it is. There is, well, it's 1658. It's off by a delta F, one sample. So that is the second order of the machine wrapped around 1800. This other peak over here is the third order. So I go through the same arithmetic, multiply the running speed by 3, subtract 1800, and then subtract that difference from 1800, and that'll put us down here at, what is it, 600 or around 600 RPM, 594. So that is the data that we've extracted from this video. Let's move on. Now we've got the same thing for the second video. It's monitored points, and I already have those results in here in the ODS from the second video. Let's go compare the ODSs. This is the so-called proof of the pudding. Let's go see what we get. And these are numerical comparisons, correlation coefficients between the ODSs at the three peaks. Here's 972, 1656, 596, which got saved off of the ODS FRS from the first video. Down here is the data that was saved off of the ODS from the second video. Little bit different frequency, not much. 972.21 versus 02, 1655 versus 56, and 591 versus 96. So if we go back and look at the delta F of the data, they're probably off by 1 delta F. Good results. And then down below are the MOCHAPE values. But over here in this picture, these are MAC values, or modal assurance criterion. Now that is a complex calculation between the ODSs from the two videos. And if they're identical, the answer would be 1. You can see the answer is 0.98, so they're almost identical. Now the MAC actually is a measure of whether or not the two shapes are parallel. So think of two lines in multi-dimensional space. Are these two lines parallel to each other? And again, we're talking about shapes in 8 different dimensions here. We got magnitude and phase in 8 dimensions at 4 different points. So what that is showing us is that, yes, these two ODSs that we got off these two videos are 98% alike in terms of their parallelism. They're parallel in n-dimensional space. 96 for the second frequency or the second order. And then over here is the third order, 95% for the third order at 600 RPM. And then this off diagonal here is basically the MAC value between the first and second ODS. One from the second video and one from the first video. Well, that can be true also, that, you know, the ODS of the second order is very similar for these 4 points to the ODS of the running speed, the 900 RPM. Here's a little more accurate measure. This is something that's unique to MEscope. We call it the shape difference indicator. Now, what this is, again, some complex math between magnitude and phase of the two ODSs, and it's a correlation coefficient too, in the sense that its values are all between 0 and 1, just like MAC. MAC is normally used for mode shapes, but it works just as well for any shape data. In this case, we're looking at ODS data. We could do the same thing. We could actually curve fit, and we did this last month in the webinar. We curve fit some ODS FRFs and got what we call OMA, or operating modal analysis mode shapes. So again, you're capturing the response, but if you don't measure the force, then you need to measure these ODS FRFs or a cross spectrum. You can take a reference and calculate a cross spectrum, which most analyzers can compute, and we also can compute that in MEscope. The problem is you can't get data in inches per second from a cross spectrum, because the cross spectrum is always the product between two responses. ODS FRF is the auto spectrum of the response of each point or each degree of freedom, and the phase relative to a reference. So a little bit different. We can integrate and differentiate ODS FRFs. You can't do that with cross spectra, but you can curve fit all of them. All right, I kind of got off on a sidetrack here, but here is the shape difference. So this is actually comparing the numerical values. Now, if we look over here in the spreadsheet, what it's comparing is magnitude and phase of the data from the two different videos. And you can see, here's the shape number 1, the running speed. The numbers are close, but different. And so this is telling us that the numbers are, again, this correlation coefficient, a little bit less than the MAC value. Here is 98%, over here is 97. But this is an even stronger indication that the video is captured. And again, we had, you know, we had different point grids from the different videos. We had different lengths of data that were processed to get the ODS FRFs, actually just different time waveforms. But this is kind of the proof of the pudding. And then there's one more command up here now, unwrap order. That was just going to change the frequencies here. I haven't got that one corrected yet. Participation is another way to correlate. Now, this is what is called a least squares fit of one set of shapes to the other set. And it's just very common mathematics between two sets of shapes. And they can be ODSs, they can be mode shapes, it can be any shape data with numbers in it. Magnitude and phase, or just magnitudes. I can compare frequencies if I store them in a shape. But this is showing that, yeah, I got a little bit of an issue here with my scaling. Let me just move this over a little bit. That between ODS the first ODS from the first video and the first ODS from the second video, if I curve fit the data from one mode shape or one ODS to the other, the number comes out a little bit greater than 1, and then these are a little bit less, 90%. Rule of thumb is anything over 90% is a pretty good correlation. Another thing, and again, I'm off on rabbit trails here, if I take these participations of video 1 into video 2 and multiply by these participations of video 2 into video 1, that is the MAC calculation. The arithmetic is the same, but anyway, that's for you mathematicians. Mark, I'm pretty much done with my presentation. Do we have any questions?
No questions at this time. We got a good math lesson there, so
Yeah,
hopefully we didn't put everybody to sleep.
I apologize for running off, but you know, there's a lot of math behind the graphics in MEscope, and as I said, it's a toolbox with a lot of tools in it, kind of like MATLAB. MATLAB, of course, has got a lot more mathematics tools in it, but in order to look at ODS data, mode shape data, and then not only from accelerometers, but from videos, MEscope is the tool that you want to own, and you want to add that option to MEscope. If you already have a license, then we call MEscope kind of a food chain. You can start out with just the basic animation of ODS data, and then add signal processing and curve fitting to get mode shapes, and now video processing to get results like I've shown you here today. All right, well, if there's no questions, we'll wrap it up, and we'll send out, I think when you make a recording of this, we'll send it out to all the attendees, and also we'll have the app note for those of you who own the license. If you don't own a MEscope license, you can't access the app notes, but you'll be able to access app note 60, which will allow you to go through all this much slower and learn for yourself what was actually done here.
Good stuff. As we mentioned before, everybody will get a copy of this webinar. You'll get an email here, probably later this afternoon. And then if you want to, you can always check into our YouTube channel, and you have a recording there as well, along with recordings of all the previous webinars. So if you got any questions, feel free to reach out to us, sales@vivetech.com. Happy to answer any questions. If you are interested in purchasing ODS videos, or you have any questions about the webinar, feel free to reach out to us and we'll get back to you. With that, stay tuned. We'll get another one of these spun up for next month, and so keep a look on your email, and we will see you next time. Have a good weekend, everybody. Take care for now.
Okay, bye.
So goodbye.